Okay, this is the centripetal force experiment. So on this experiment, we're going to calculate centripetal acceleration and centripetal force. So this is Newton's second law, which can also apply for centripetal acceleration and centripetal force. Our goal is to calculate the centripetal force and compare it to the spring force. So centripetal means center seeking. So it's the force that causes anything to stay in some type of circular motion. So in this case, the spring is going to be the source of that. So it makes sense to compare our calculated centripetal force to a calculated spring force. Okay? So we have this experiment set up here. We have this rotating platform, we have this rotating mass, and we have our spring. We have this indicator rod. So the first thing I did before I attached the spring, this is just hanging there, and I aligned it to this indicator rod. So we know our indicator is our 0 point, our equilibrium point, if you will. Okay? So now I attach the spring, and when we start collecting our data, we're going to be rotating it like this. But before we do that, we want to calculate the spring force. So that's where we have these weights here. So I have this string, and we have this pulley here. And what I did is I added weights previously to this hook until it aligned with the indicator rod. See, that's still a little bit off, so I can adjust that. I can get a little bit closer to that value that we want. Okay, so that looks a lot better. It's aligned back at our equilibrium point. So we have some mass here. It looks like about like 500 grams, so 0.5 kilograms. So that's the weight, or that's the mass of this, and we know the weight of it is 0.5 kilograms times 9.81 meters per second squared to give us our weight in newtons. So our weight in newtons is shown here, mg. Now that should be equal to the tension in the string up here, since it's not accelerating, and ignoring that pulley, that should be equal to the tension in the string here, which should be equal and opposite to the spring force. So therefore we can, with some reasonable certainty I suppose, we can say our spring force is equal to mass times gravity, and that's the mass that was on the hook. Okay? And we're going to compare that spring force to our centripetal force. Okay, so how do we collect our data? So to get a centripetal acceleration, we need velocity and radius. We can measure the radius, so we need velocity. So in order to get velocity, what we're going to do is measure the period of rotation. So period is the time it takes to rotate one time around. So for the experiment here, that will be the time it takes as it rotates one circle around like that, okay? So that will be in seconds per cycle. So let's go ahead and collect some of that. So what I'm going to do is rotate it, and now we have to get it back to our indicator rod. That's our equilibrium position. Okay, so that's all of our measurements will be taken there. So that looks pretty close. It's a little large at the moment, and then it slows down as it rotates. Now it's right pretty close now. So I'm going to hit collect on this. We get some oscillation function, some type of sinusoidal function. And while we're collecting, I'm going to keep it rotating so it stays over the indicator rod. Okay? So now it's done collecting. So the period is the time for one rotation. So that's this time that I just highlighted there. Somewhere around 0.88 seconds. But we don't know if that rotation was perfect or the better value or not. So we're going to highlight much more. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 oscillations. So we can read off the time here, 8.61 seconds. That's the time for 10 oscillations. Okay? So we can divide that by 10 to give us our period of rotation. That's kind of an average of all 10 rotations. Okay? So from period, we can calculate speed. So we know the period is the time it takes to rotate one rotation. Well, to find velocity or speed, we know it's the change in distance over change in time. Well, how much distance does it travel? Well, one circumference of a circle. So for one circumference of a circle, it traveled one period of time. So distance over time is circumference over period. So we can calculate our velocity, and then velocity and radius, we can calculate our centripetal acceleration, and therefore calculate our centripetal force. And we will compare our centripetal force, as I mentioned, to our spring force, as shown over here. Okay? So as for our experiment, we will do that, and we will change the rotating mass. So we're going to do 7 trials. We will do 7 trials, and we will find an average centripetal force, standard deviation of the mean. And we'll use that to compare it to our spring force. Okay, so on our experiment, we're going to repeat the experiments. Okay, so on the next time we're going to change the rotating mass. So right here we can add some additional mass to it. Okay, and repeat the experiment. Alright, so we'll repeat all the steps of the experiment, calculate the spring force, do all 7 trials, calculate the centripetal force, and we'll do the experiment again. And yet a third time. On the third time we'll change the radius, so we'll have to adjust the length of this bar and adjust our indicator rod to refine our 0 or equilibrium point. Okay, so each time you do this experiment, it should be treated separately as its own individual experiment. Okay, so we're going to try to determine by changing the mass, and then again by changing the radius, what's that going to do to our results. Okay, and what changes, what doesn't change. Is our spring force going to change on each time? Possibly. Is our centripetal force going to change each time? Is our period? Is our centripetal acceleration? So we have to think about all these using our equations, okay? So we'll have to use our equations here to think about what is changing in the experiment and what has stayed the same, and each time comparing our centripetal force to our spring force. Okay, so that is a centripetal force experiment. Thank you.